Okay, so find the length of the curve for this y squared equals 4 times the quantity x plus 4 cubed over the interval x between 0 and 2 for y values being greater than 0. So we know that this is not this has two pieces involved because there's a y squared, so it's not a function, but they want us to restrict it to y being greater than 0. So we will eventually, I guess, go take a look at the graph also. Let's just go about finding the length of the curve using the formula we developed earlier. So here I'm thinking it's easy to isolate y, so I'll go ahead and isolate y and then I guess keep the top half because they said for y greater than 0. So we'll take square root of both sides. We could isolate x, but it seems easier to isolate y in this case. So I'll take square root of both sides, and y is equal to plus or minus. Since this is a product, I can split it into two pieces. Square root of 4 is 2, and then I have x plus 4 cubed under the square root. So how about we just end up keeping the positive y's. So y equals 2, and I'm going to write this as x plus 4 to the 3/2. The root is a square root and the power is a 3, so this square root of x plus 4 cubed could be rewritten as a fractional exponent. It might make it easier to differentiate. So I'm going to use this as a function of x, y as a function of x, over the interval between 0 and 2. And since y is isolated and I have x values, I'm probably going to go ahead and set up a dx arc length problem. So I'm going to do what we call the type 1. So I'll go ahead and find y prime or f prime first. So 2 times bring down the 3/2, x plus 4 to the 1/2 times, even if I do a chain rule, the derivative of inside is 1. Let's clean it up a little bit. So we got our y prime. Now you're going to find or figure out y prime squared. So we're going to square this guy. So squaring the derivative gives me 9x plus 36, and I'm going to go ahead and put it in here and set up a dx problem. So our arc length from 0 to 2, remember they have to be x values because I'm doing a dx problem and everything is in terms of x's, and they were telling us to look at it over this interval from 0 to 2. So let's go clean this up and integrate that. It doesn't seem to be too bad, a basic u sub it looks like. So it's just a simple square root function, and looks like I have dx is du over 9, so I have my du over 9 taken care of and square root of u. I'll go ahead and change my limits of integration so I don't have to worry about them. If x is 0, I put in 0 for x, and the bottom limit is 37 it looks like. And if x is 2, I put that in here. 9 times 2 is 18 plus 37, that's 55 for my upper limit. So that's just u to the half, and we're going to integrate that and get u to the 3/2 times 2/3 with the 1/9 that was out in the front. Let's plug in our limits of integration. So that's basically the arc length in exact form. This is how long the curve is over the interval 0 to 2. And let's go see what approximately that is and if that kind of makes sense graphically. So if I punch that into my calculator, it's approximately 13.5 units. And I'm going to go back and look at what this guy looks like on my TI. So we had something that was not a function, y is a function of x. We isolated y and kept the top half of it because they said for y greater than 0. So I should be able to punch this into my TI and take a look at what it looks like between 0 and 2. And see if it kind of makes sense that I might have 13.5 units for that length. So I got 2 times the quantity x plus 4 raised to the 3/2 on my TI. Let's go do a zoom standard first, zoom 6, to see what that thing looks like. So it looks like I'm interested in what happens between 0 and 2, and that means it's way up there, so let me go up higher to see what happens. So I just made my window. I pushed window between -1 and 3 because I want to get an idea of what happens between 0 and 2. And then y min I made 0, and y max I just picked 35. Let's see if that gives me a high enough window. So it looks quite linear. Between 0 and 2, we're interested in this length, and we're getting that length. There is some curvature involved, of course. That length is 13.5. Let's see if the 13.5 makes sense. Okay, so let's do second trace and put an x value. We're going to push 1. And what x value? We want an x value of 0. I'm pushing 0. Let me get this up. I push 0, push enter. And it looks like, oops, I have 0.16. And then let's go put second trace, enter 1, a value of 2. Let's see where 2 is. And 2 lands us here at 2 and about 29, let's say. So at 0.16 to 29, and we were interested in this arc length. So even if we don't do much, and if we just look at the difference of 16 and 29, notice we get about 13 there. So if this were just a length straight up in the air, there's a difference of about 13 units. So like even if I approximate it to be linear, I know I'm looking between 0 and 2 for the x values. That's 2 units horizontally, and I've gone up about 13 units vertically. So even if I say it's something linear, that's going to give me 13 squared plus 2 squared, which actually if you punch it into your calculator, you're going to get approximately 13.2. So even if these guys were linear, like segments, that region would be 13.2, and we looked at the graph that it behaved almost linear, but there is some curvature involved, we know that. So that contributes another approximately 0.3, I guess. So we get this length approximately 13.5, which makes sense based on our analysis. So that's just a reassurance. But if exact value is asked for, this is what we would give. But it's good to see if things make sense or not. Let's go look at another example. Find the arc length of the curve y squared equals x cubed between 1, 1 and 4, 8. So in this case, they're just giving us two ordered pairs that the curve satisfies. They're not telling us whether I should use x values or y values, so whether I should set up a dx problem or a dy problem. So I have options. So my options are that I can isolate y here and use x from 1 to 4 and set up a dx problem and find my arc length. Or I can isolate x, because that's also easy to do here, and then have my y values from 1 to 8 and do a dy problem. And regardless of which I use, I better get the same arc length. So let's go ahead and try both. Sometimes one ends up being an easier integral to evaluate rather than the other, but we'll set up both and see where it takes us. Okay, so I'm going to isolate y for the first option, square root both sides, and we get y is equal to x to the 3 halves, and I'm just going to use y equals x to the 3 halves, the positive portion, because notice my y values are positive, so I'm looking at the top half of this graph. So I went through my steps. Find y prime, I found it. Find y prime squared, I squared it. Use the formula, and we're doing a dx problem because I have a function of x that I chose to work with. So I used my limits of integration to be the positive 1 and the positive 4, the x values for the dx problem. And that doesn't look too bad. That looks like it's just a u sub again. It's a square root function, so let's go quickly integrate that. I chose to get a common denominator of 4. You don't have to do this, and clean it up a little bit. I split up the square roots and took out the 2 and made a 1/2 in the front. I'll go do a u sub quickly. So u is 4 plus 9x. I have a half, and du over 9 was my dx. I pulled a 1/9, square root of u, change my limits, put in a 1, and we get 9 and 4 is 13. Put in a 4, we get 36 and 4 is 40. So I integrated u to the half, u to the 3 halves times 2/3 from 13 to 40. We put in our values, and we get this exact answer, or if we punch it into our calculator, we get approximately 7.6 units for that arc length. And again, all of this was a simple u sub. We could also use our TI to punch that in and see what value we get right off the bat if an exact answer is not required. So let's go do that quickly to make sure everything is okay. I'm going to turn this on. Let's get out of here. And let's go Math 9. Math 9 will give me the option to integrate. So I'm going to integrate this function. Integrate the square root of 4 plus 9x. I'm going to take care of the half at the very end. I won't involve it right now. Comma. X, because I'm doing in terms of x, comma, the limits of integration 1 to 4, 1, comma, 4, close that up, enter, and then divide that by 2 because of the half I had outside. And notice I showed all the work and got the exact answer if it was required, but as an approximation quickly, I see that it is 7.6 units, approximately to 1 decimal place. Now this was having done the problem with a dx integral and isolating y. Now let's go do option 2 and isolate x and see if we get the exact same thing and how the integral looks. So let's go isolate x, we said this time. So I'm going to raise both sides to the 1/3, and I have x equals y to the multiply powers. 2 times a third is 2/3. So there is the problem I'm going to deal with now and differentiate this business. This is x as a function of y. Alright, x is isolated, x prime or dx dy is bring down the 2/3, subtract 1, and that's going to be a negative y to the negative 1/3, and I wrote it in the denominator. I'm going to go square it. Okay, so square the 2, 4, square the 3, 9, and square the 1/3, that's going to be 2/3, and let's go plug it into the formula. Remember, this is going to be a dy problem, so I better use y values for my limits of integration, 1 to 8. So 1 to 8, square root of 1 plus f prime or x prime in this case squared, and notice that integral does not look as friendly as the dx problem we had set up. But nevertheless, let's clean things up a little bit and see what it looks like, and then we can go ahead and quickly set it up by hand and also use our TI and hope that we get the same arc length. So again, I got a common denominator of 9y to the 2/3, multiply top and bottom of 1 by that, I get this. It looks like this is a perfect square, so let's split up the radical. So I have 3 square root of 9 that pops out, and then y to the 2/3, its square root will pop out y to the 1/3. And in the numerator, I can't split them up any further because it's a sum, so they're stuck together. So now I have an integral that does not look that nice, but I should still be able to do it, I think, with a u sub. Let's try the u sub and let u be this guy, because I'm thinking if I let u be this guy, its du is going to pop out a y to the negative 1/3, which will pick this guy up maybe. And yep, it sure looks like it does. If I let u be this guy, my du will be this guy here, and then I end up with a 6, and I can take this downstairs. Y to the 1/3 in the denominator and a dy do get picked up by that business. So let me divide both sides by 6 and also maybe pull out a 1/3. So that doesn't look so bad. I pulled out the 1/3 in the front, and I got a du over 6 that gives me my dy and the y to the 1/3 in the denominator. So I also pulled out that 1/6, and I simply have square root of u du. These guys got picked up. And my limits of integration, if y is 1, I have y to the 2/3, or 1 to the 2/3 is just 1. 9 plus 4 is 13. And if y is 8, I have 8 to the 2/3, which will give me 4, and 9 times 4 plus another 4 is 40. So after this, we know what to do. That's just a simple square root to integrate. So let me put this guy into my TI and see if it actually gives me the same arc length as before. Or you could do this by hand. Okay, so I have the square root of x function in terms of x from 13 to 40. Let me push enter. I get that guy, but it's 1/18 out in the front, so I divide it by 18, and good news, we get the same thing. So doing a dy problem gave me the same 7.6 that I ended up getting with a dx problem. But notice the dx problem gave me a much simpler integral to deal with, a simple u sub, as opposed to this u sub that was a little bit ugly with the algebra and fractional exponents involved. So the point is, you could set up a dx or a dy problem And it doesn't matter, you're going to get the exact same arc length either way.